Have you ever stopped and wondered what's really going on inside the AI you use every single day? Well, it turns out there's this one single revolutionary architecture that powers pretty much all of it. It's called the transformer. And in this quick explainer, we're going to pull back the curtain and see exactly what makes this hidden engine run. It really all boils down to this one question, right? When you type something in, how does an AI actually get the context, the nuance, the relationship between all your words? That's the puzzle. You know, if you've ever been amazed by how ChatGPT can remember something you said 5 prompts ago, well, that's not magic. That's the architecture we're about to unpack. And this isn't just about text. Nope. This exact same fundamental design is what lets models like DALL-E understand your wild descriptions and somehow turn them into incredible images. It's not just one company's secret sauce either. Other huge players, like Anthropic with their model Claude, they rely on the same core design for all those powerful reasoning and writing skills. And this thing's reach goes way beyond the creative, deep into complex science. You've heard of AlphaFold's groundbreaking work predicting protein structures, right? You guessed it, powered by the very same idea. So yeah, all of these amazing tools, they're all connected by one thing, the transformer architecture. This is the design that completely changed the game for AI, and today we're going to see exactly how it works. Okay, so to really get why the transformer was such a big deal, we got to look at what came before it. We're talking about recurrent neural networks, or RNNs, and more importantly, why they just kind of hit a wall. Just think of an RNN like it's trying to read a sentence through a tiny peephole. It sees the, then it scoots over to animal, then didn't, and so on, one at a time. At each step, it's desperately trying to pass a little summary of what it's seen to the next word. But this one-by-one process, it creates a huge bottleneck. As the sentence gets longer, that context from the beginning just starts to fade away. This whole approach created 3 massive roadblocks. First, that bottleneck problem, where the entire meaning of a paragraph had to get squeezed through one tiny point. Second, what we can call the sequential trap, which just made it painfully slow since it couldn't look at all the words at once. And finally, this issue called the vanishing gradient. It's a fancy term, but all it really means is that by the time the model got to the end of a long sentence, it had pretty much forgotten how it even started. The solution wasn't just a small tweak. It was a complete paradigm shift, a totally new idea that basically said, hey, what if we don't have to process words one by one? This, my friends, was the attention breakthrough. And this slide right here perfectly illustrates the difference. RNNs were basically playing a game of telephone, where the message gets weaker and all distorted as it's passed down a long line. Transformers, on the other hand, well, they're like a room full of conversations. Every single word can talk directly to every other word all at the same time to figure out the real context. It's a total game changer. So, how in the world do you build this room full of conversations? Let's take a look under the hood at the core pieces that make the transformer tick. The absolute heart of the transformer, the one big idea, is a mechanism called self-attention. This is the magic that gives every single word the power to look at all the other words in the sentence and decide for itself which ones are most important for understanding its own meaning. So let's take this sentence. The animal didn't cross the street because it was too wide. An older RNN might get super confused. Is it the animal or the street? But with self-attention, the word it can instantly scan every other word and calculate that, yeah, its meaning is way more connected to street than animal. That's the power of making those direct connections. Now, transformers take this a step further with something called multi-head attention. The best way to think about this is like having a panel of experts all looking at the same sentence at the same time. One head might be an expert on grammar, another is just focused on who did what to whom, and a third might be tracking the overall theme. They all work in parallel, and together they build a much, much richer understanding of the text. Okay, but wait, if all the words are being processed at once, how does the model know the difference between dog bites man and man bites dog? The meaning is totally different. That's where this clever trick called positional encoding comes in. It adds a unique mathematical signal, kind of like a zip code, to each word, telling the model its exact position in the sentence without having to read them one by one. All right, so here's a really fascinating part of the story. The original transformer paper, back in 2017, actually laid out a 2-part system, an encoder and a decoder. But over time, researchers realized they could split it apart, and that created 3 distinct families of models that we use all the time today. This split gave us 3 specialized groups. First, you've got the encoder-only models, like Google's BERT. These are designed to understand text deeply. They look at a whole sentence at once from both directions, which makes them perfect for things like search. Then you have the decoder-only models, like GPT. These guys are masters of generation. Their one job is to predict the very next word, which is why they're so good at chatbots and writing. And finally, you have the encoder-decoder models that use both parts, making them ideal for tasks that transform text, like translation or summarization. Now, let's just talk about scale for a second. The very first GPT model had 117 million parameters. Now, you can think of parameters as all the little knobs the model can tune to learn patterns. And back then, 117 million was a very, very big deal. But then GPT-3 came along with 175 billion parameters. Just let that sink in. And at this mind-boggling scale, something totally incredible happened. The models started showing what researchers call emergent abilities. These are skills it was never explicitly trained for, like writing code or reasoning through complex problems, all just from seeing a few examples in a prompt. It was wild. So this all leads to a really key question. Out of those three families, why did the decoder-only architecture, the one GPT uses, become the blueprint for pretty much all of today's most powerful and famous AIs? Well, it really came down to a philosophy of less is more. First off, it's just plain simpler to build and scale one massive stack of components instead of two. The simpler design also turned out to be incredibly versatile. It could both understand context and generate new text really well. But most importantly, it was in these massive, simple, decoder-only models that those jaw-dropping emergent abilities really started to pop. On top of all that, they were even more efficient to train. So, let's just wrap this all up. The Transformer's big trick, processing everything at once and letting every word talk to every other word, wasn't just a small improvement. It was a complete reimagining of how a machine could understand language. It really truly is the backbone of all modern AI. This whole architecture was built to master sequences. Sequences of words, of pixels, of amino acids. But looking ahead, it leaves us with a really fascinating question to chew on. What new breakthroughs are going to happen when AI finally figures out how to move beyond the sequence altogether?
If you found this helpful, hit subscribe and the bell so you never miss a video.